Okay, next section is 1.7. We're going to model with functions in this section. What you're going to learn about is how to find functions from formulas, from graphs, verbal descriptions, from data. And the why is that using a function model under observation in terms of another variable allows us to make predictions about the future events of a certain situation, which obviously has a lot of real-world applications. So, constructing function, let's start off with an example of finding a maximum. Okay, so what we have is we have a square of side x inches that's cut out of the corner of an 8-inch by 15-inch piece of cardboard. So I'm going to draw a picture here. We have a piece of cardboard that is 8-inch by 15 inches, and we're going to cut out these corners. And that amount we're going to cut out, we're going to call x, right there. We want a volume function. Okay, so volume is length times width times height. So the volume of this box in terms of x would be, the length would be 15 minus 2x. The width would be 8 minus 2x. And the height would just be x. When you fold this little part up, the height would just be x. All right, so there's our volume function in terms of x. We're going to find the domain of this thing. So the domain now is, I can use all real numbers for this, but I can't go negative, obviously, in this situation because we can't cut out a negative amount. And then also, we got to think about the maximum amount that we can cut out. You know, x, if you cut out a lot, you know, you can cut out a ton so that you only have this little small little base right there. And obviously that would be, you know, you have to cut out less than half of 15 here. You can't cut out 7.5 because you wouldn't have a base left. So the domain would be, you know, obviously we got to be bigger than or equal to 0, but we also have to be less than or equal to 7.5. Now we can write that as an interval notation. I'm sorry, parentheses, because we can't actually have 0 and we can't actually have 7.5. So that would be our domain. All right, and then we want to graph this over the domain and use the maximum finder on our grapher to find the maximum volume. How much would we cut out to find the maximum volume? So let's just graph this equation in our graphing calculator or on Desmos. I'll just use the graphing calculator right here. So under y equals, actually I got to change mine back into function mode. And I'll just type this in. I don't have to distribute it. 15 minus 2x times 8 minus 2x times x. I don't need that in parentheses, but oh well. All right, so let's graph it. We're going to have to change the axes quite a bit here. I'll try zoom fit and see if that helps us out at all. But obviously the volume's going to get really big, so we're going to have to go up quite a ways. So it looks like I can already see one branch going up, one branch going down, so the maximum should be up there somewhere. So one thing I can do is just go to window and change the y value to go up quite a bit. But I'll try zoom fit first. Zoom fit is zoom 0. And that didn't really help me much. Well, I need this point up here. So I'm just going to go to my window, and I'm going to do X max and make that much bigger so that I can see this thing. Min, I don't care as much about the min. I'll do negative 100, and I'll do like 500 here. I don't know. Just take a look at that and see what we see. All right, so that's good enough. Not perfect, but we'll do second calculate maximum, and we'll find that maximum. Enter, enter, and then enter for the third time, and we get about 1.6 repeating and 98.74. So 1.6 repeating, 98.74 for volume. So that's the maximum, that's the amount we cut out to maximize volume, and that's the volume that we get. Okay, you can find the other dimensions for width and length too from this formula now that you have these ordered pair. You know, plug in x for this part right here, and you'll get the length. Plug in x for this part, you'll get the width. And the height, you know, is going to be 1.6 repeating to maximize the volume. Okay, so there's an example of like how you could apply this to find maximum volume. Here's another example. Let's say grain is leaking through a hole in a storage bin at a constant rate of 5 cubic inches per minute. The grain forms a cone-shaped pile on the ground below, so let's draw a cone. As it grows, the height of the cone always remains equal to the radius. So we know we were just given the height has to equal radius. If the cone is 1 foot tall now, how tall will it be in an hour? So we're starting at a height of 1, so I'll call it h sub 0. And the question is, what will h be after 1 hour? Okay, so what we can do is set up a volume equation. They gave me a volume rate increase, so I want to set up a volume equation. Volume of a cone is 1/3 area of the base times the height. The area of the base, though, is pi r squared. And we're told the height equals the radius, so I'm just going to plug in, for h, I'll plug in r. So that'll make it r cubed. So there's a simplified formula for volume in terms of r. Now the initial volume I'll find, I know the volume's changing, so the initial volume is changing plus a rate of 5 cubic inches per minute. So if I multiply by t then, time, in minutes, the minutes would cancel and I get a volume increase. So I don't know why I wrote radius. The volume is increasing at a rate of 5 cubic inches per minute. So if I multiply that by time, that will give me a volume increase. All right. Now, I need to find the initial volume at 1 foot because that's what they say the original height and radius are, obviously. They're equal. I'll use 12 inches, though, because I'm doing this in inches, so I've got to stay in the same units. So, original volume is 1/3 pi r cubed again. So it's 1/3 pi, and then r started off at 12 inches, or 1 foot cubed, plus 5 times t. Now, they said after 1 hour, so 1 hour would be 60 minutes, so I'm going to do 60 right there for that t. Equals 1/3 pi r cubed. So they want to know the new radius after an hour, 60 minutes. So I'll just solve this equation. I would just multiply this whole thing by 3 to get rid of this 1/3, and I would divide the whole thing by pi, and then take the cube root. So then raise this whole thing to the 1/3 power in your calculator, or take the cube root. That'll be r by itself. If you do that, you should get. I got a radius of 12.6 inches. Okay, constructing a function from data is another problem that we can try. So if you want to do this, you can plug this in your calculator. Here's an example. Table shows the number of patent applications in the United States from 1993 to 2003. Find the linear and quadratic regression, which appears to be the better model. So in the calculator, you probably remember this from Algebra 2. You go to Stat, and you go to Edit, and you can edit this into a list in your calculator. Well, I called 1993 year 1. I could have called it year 0. Doesn't matter. And then I put my Y information into my L2. Then I went to Stat, calculate linear regression first, and just hit Calculate. And it gives me this. Now, if I turn my diagnostic on, I'll get an R value here as well. Just go to Catalog, second Catalog, turn Diagnostic on. But there's my equation, 19.23x and 157.8. 19.23x plus 157.28. There's my equation that's linear. Now, you can do this in Google Sheets as well, which we've been using quite a bit. It's actually pretty easy. When you insert the table, just do a table of values just like that, like I did in the calculator. Highlight the table of values, go to Insert, and then do Chart. Now pick a scatter plot, that one right there, hit Insert. And then once you get it inserted, I've already got one here, so let me do this one. Once you get it inserted, go to Advanced Edit and scroll down to the, you can edit all this, it's very user friendly. But down here when it says trend line, you can choose to do a linear, exponential, polynomial, but choose linear for the first one. I'm change the label to use equation, so that actually gives you the equation. You'll see it gives you the exact same equation. You can also do polynomial and degree 2. That will give us a quadratic, and then use equation, it gives us that equation. So you could do both Google Sheets and with the calculator. Obviously with the calculator, you go back to Stat, you go to Calculate, and you do quadratic regression, which is 5. And then hit Calculate, and you get the same thing. Now, you also want to look at your R value. So this gives me, I have the R value here. It says show R value on Google Sheets, and it gives you the R value of 0.96 0.969. Calculator will do the same thing with the diagnostic, like I said. So if you want to, you can compare the 0.969 to what you had with a linear, and that was 0.957. So the quadratic's a better fit because the r value is closer to 1. So, you know, if you look at this polynomial second degree, the 0.969 is closer to 1, therefore that's a better fit. So we would choose a quadratic relationship to represent this data. Okay? The last thing is just these functions to review. These are functions, there's 10 of them that are going to be major functions you're going to want to be familiar with. And this is a summary that the book gives as far as what chapter they're found in. We have obviously linear, obviously quadratic, cubic. Quartic is basically the same shape as a parabola. Also, natural function. The natural function goes like this. Exponential, up like this. Exponential, if you have a b that's between 0 and 1, is exponential decay. Power function, logistic function, which is the limit to growth, and sinusoidal, both cosine and sine. All right, let's try some Weber problems. Hopefully this helps.